Okay, so the topic of today is that we will be studying some basic properties of SLE. The main tool we'll be using will be Loewner chains. And just like yesterday, Mattis Lemkuller will be looking in the chat and he will answer any questions that you may be having. Today's lecture will be quite independent of the third lecture on Thursday, so it's still possible to come on Thursday, although you don't follow everything in today's lecture. Today's lecture will probably be the most technical one in the mini course in the sense that it contains the most proof. So the lecture on Thursday will again be far less technical. Yeah, so as I mentioned, the main tool we'll be using today is the Loewner equation. And one important message today is that the Loewner equation is very useful to study SLE because it allows us to study SLE by using stochastic calculus. So by the Loewner equation, we know that an SLE is encoded by a Brownian motion. So the Loewner equation is allowing us to transform this complicated two-dimensional path into some one-dimensional object, which is very well understood. So I will start by recalling a little bit of what we did yesterday. So yesterday I was telling you that Schramm introduced SLE because he was interested in studying conjectural scaling limits of a number of discrete models. And one of his realizations is that instead of studying the curve eta, he could study the driving function w of eta. And he also realized that certain natural properties of eta implies that w has to be a multiple of a Brownian motion. Then I also defined SLE. So I defined SLE by solving this Loewner differential equation where the driving function is given by the square root of kappa times the standard Brownian motion. Then I defined SLE in some general simply connected domain D via a conformal map. And then we were looking at conformal invariance and the domain Markov property, and we were looking at Schramm's theorem, which is saying that if we have some probability that the curve is under some conditions, it is an SLE. If and only if it satisfies two properties that are known by conformal invariance and domain Markov property. And then to get some discrete intuition, I was explaining what conformal invariance means in the setting of percolation. So that's where we ended yesterday. And then today, I will start by giving some discrete intuition for the domain Markov property. So conformal invariance is often very difficult to prove for discrete models. But the domain Markov property, on the other hand, is often holding in an exact way in the discrete, and therefore we know that if the model we study has a scaling limit, then we know that this model also has to satisfy the domain Markov property. So for example, percolation is satisfying the domain Markov property. So here we have a percolation interface. We have stopped it after the first 25 steps. And then we're looking at the law of the rest of the curve conditioned on the initial segment. So the part of the domain which has been covered by the curve, we call it K sub 25. Then we observe that our domain D minus K25, that's also a simply connected domain. We see that this domain has two marked points, eta of 25 and B. And we see that the rest of the percolation interface is simply the percolation interface on the domain D minus K25 with marked points at eta of 25 and B. So we see that, and we can use this to deduce that percolation satisfies the domain Markov property. So another model which satisfies the domain Markov property is the self-avoiding walk. So it can be proved that the number of length n self-avoiding paths on 2 from the origin, that's approximately equal to mu to the power n. So here mu is the constant which is known as the connective constant. So proving the existence of a parameter mu such that the result in the first bullet point is holding, proving that is not so hard, so that can be done by subadditivity. But computing the value of mu is a very hard open problem, and the best known rigorous bands for mu are shown on the slide. It's also conjectured more precisely that the number of self-avoiding walks is mu to the power n multiplied by some power law correction, where the power in the power law is universal, while this constant mu is lattice dependent. Okay, so to define the self-avoiding walk, we assume that D is a simply connected domain with marked boundary points A and B. Then we let DM, A, and BM be some discrete approximation to this domain. For example, we can assume that we can consider some rescaled version of Z2. Then we can let D sub M be the set of lattice points contained in D, and we can let AM and BM be approximations to A and B. The exact definition is not so important as long as AM and BM are connected in DM. And then we say that the self-avoiding walk, it's a random path such that the probability that this random path is equal to some fixed path little w is proportional to mu to the power the length of w. So the self-avoiding walk is very easy to define, but it has turned out that it is very difficult to analyze rigorously. And it is conjectured but not proved that the self-avoiding walk is converging to SLE with parameter kappa equal to 8/3. So this self-avoiding walk is satisfying the domain Markov property. So if we condition on the first k steps of the curve, then the law of the rest of the path is that of a self-avoiding walk in the domain we get by removing the initial segment of the curve. So I've left the details of this proof as an exercise, but it's almost immediate from the definition of the self-avoiding walk. Okay, so then I will start to prove one direction of Schramm's theorem. So I will argue that if we have I will argue that SLE is conformally invariant and satisfies the domain Markov property. So conformal invariance is just immediate from the definition of SLE, since we defined SLE in the general domain via a conformal map. Justifying that the domain Markov property holds requires a bit more work. So what we want to prove, so we want to run the SLE until some stopping time tau. Then we condition on the initial segment of the curve, and we want to show that the SLE in the domain we get by removing the initial segment has the law of an SLE in that domain. Yeah. So we want to we condition on the initial part of the curve. We want to show that the rest of the curve has the law of an SLE in the domain we get by removing the initial segment. So in the setting of the figure, we want to show that the red dashed curve has the law of an SLE in the slit domain obtained by removing the initial part of the curve. Okay, so what we want to prove is that the red dashed curve. Before I continue, I can also mention that it's sufficient to verify this for SLE on the upper half plane and parameterized by half plane capacity, because the domain Markov property holds in this setting if and only if it holds in the general setting. So what we want to show is that the red dashed curve in the left figure has the law of an SLE in the slit domain. By conformal invariance, this is equivalent to showing that the curve eta hat tau in the middle figure has the law of an SLE in the upper half plane. The left and the middle figure are related by a conformal map, G tilde, which we call the centered mapping out function at time tau. So you remember that when we map out the SLE by the standard mapping out function, then the tip of the curve is sent to some random point, W of t, on the real line. And the center mapping out function is defined by considering the standard mapping out function minus W of t. So it is defined such that the tip of the curve is mapped to the origin. And since the standard mapping out functions satisfy the Loewner equation, it's not hard to show that the centered mapping out functions satisfy the centered Loewner equations shown by in the indented equation. So then I have left most of the proof as an exercise. But if you do these exercises, then what you will see is that if you define G tilde sub tau comma t to be the center mapping out function of eta hat, eta hat tau, then these centered mapping out functions, they satisfy this centered Loewner equation, and they satisfy the centered Loewner equation with the same driving function as for the original curve, except that the driving function has been recentered at time tau. So this implies the desired result that eta hat tau has the law of an SLE, and that is because eta the centered mapping out functions of eta hat tau, they satisfy the Loewner equation by a driving function which has the law of a Brownian motion. And we see that the driving function has the law of a Brownian motion by the Markov property of, by the strong Markov property of W, which holds because W is the multiple of a Brownian motion. Yeah, so this justifies that SLE is satisfying the domain Markov property. So then we will be proving Schramm's theorem in the other direction. So we assume that we have a family of probability measures on curves. So for each simply connected domain D and boundary points A and B, we have such a probability measure. And we assume that our curves satisfy conformal invariance and the domain Markov property. And we want to prove that our curves are SLEs. So we let eta be a curve sampled in the upper half plane, and we assume it's parameterized by half plane capacity, and we let W denote the driving function of eta. So then the strategy of the proof is to see what these two properties, conformal invariance and domain Markov property, is telling us about the driving function W. And what we will see first is that conformal invariance is implying that that W is satisfying Brownian scaling. So what we do to prove this is that we first define eta tilde to be a rescaled version of eta. So then we know that eta is equal in law to eta tilde. So how do we know this? So we know this by conformal invariance because the map which is sending z to r times z, that's a conformal map. So then it's also possible to let g tilde denote the mapping out functions of eta tilde, and one can argue that these mapping out functions satisfy the Loewner equation with a driving function, which is a rescaled version of the original driving function. So I will not show the details of this now because the exact same argument was applied when we proved scale invariance in law of SLE. So we see that eta and eta tilde, they are curves with the same law. Both of them have a mapping out function satisfying the Loewner equation. And since the curves have the same law, then the driving functions must also have the same law. So this implies that the driving function is satisfying Brownian scaling. So then we look at the domain Markov property, and again we will try to figure out what the domain Markov property is telling us about the driving function W of eta. So first we recall what the domain Markov property is telling us. The domain Markov property is telling us that if we condition on the initial segment of the curve, then the rest of the curve has the law of the curve sampled in the domain we get by removing the initial segment of the curve. Okay, so so in other words, we know that the dashed red curve in the left figure that has the law of a curve sampled from our measure in the slit domain. So then by conformal invariance, this implies that the curve in the middle figure, eta hat s, has the law of a curve sampled from our measure mu in the upper half plane. And we can also, by the Markov property, we also know that the curve eta hat s is independent of the initial segment of the curve. So then the second of the smaller bullet points that follows from our proof that an SLE satisfies the domain Markov property is proved by the exact same argument. So by combining the two small bullet points, then we see that that W, the driving function W, must have independently distributed. They must have identically distributed increments. So that follows because the curve eta hat s is equal in law to the curve eta, which implies that the driving functions also must have the same laws. Since we know that eta hat s is independent of the initial segment of the curve, we can also deduce that the increments of w are independent. So what we see is that conformal invariance implies Brownian scaling, the domain Markov property implies that W has IID increments, and the unique continuous process satisfying these two properties is, so the unique processes are constant multiples of a standard Brownian motion, So this proof is exactly what made Schramm realize that SLE curves had to describe the scaling limit of the discrete models that he was interested in. Okay, so this is concluding the proof of Schramm's theorem. So the next result we will be looking at is phases of SLE. You remember that an SLE is constructed where it can be sampled by solving the Loewner differential equation, where the driving function is root kappa times a Brownian motion. And it turns out that the properties of the SLE depend very strongly on the value of kappa. At first, this is maybe surprising because if you look at the driving function, then it doesn't have any phase transitions as we vary the value of kappa. But for the SLE curve, we do have such phase transitions, and we have such phase transitions at kappa equal to 4 and kappa equal to 8. So when kappa is equal to 4, then the SLE curve is simple. When kappa is between 4 and 8, then the curve is self-intersecting, so it hits its past. And every time it hits its past, it's bouncing off again without crossing. So this middle figure is showing you what such an SLE, roughly speaking, can look like. So we see that it hits its past and it's bouncing off again every time that this happens. The SLE for this range of kappa values is still having 0 Lebesgue measure. So when kappa is bigger than or equal to 8, then the SLE is space filling. So it means that the SLE curve is hitting every single point of the domain. It's still a curve which is continuous and a curve which is never crossing its past, but it's still a curve which is hitting every single point of the domain. In the figure, then the SLE curve is first visiting the regions which are colored in red, then the orange regions, then the yellow regions, the green regions, and finally the blue regions. And I want to show you a simulation of the space filling SLE, which is made by Jason Miller. Here you can see a simulation of an SLE with a parameter kappa equal to 128. So the black points, that's the set of points which have not yet been hit by the curve. And by the color points are the points which have been hit. And you can see that the curve is starting at the midpoint of the upper boundary and ending at the midpoint of the lower boundary. So I will not give a full proof of this theorem, but I want to prove that there is a phase transition at kappa equal to 4, and that this is the point where the SLE goes from being simple to being non-simple. So we will be proving the first lemma stated on the slide, which has that SLE is simple for kappa between 0 and 4, and otherwise it's not simple. So this will be deduced from the second lemma on the slide. That's saying that kappa being between 0 and 4 is equivalent to a certain stopping time being finite almost surely. So the stopping time, tau sub x, is defined for points x on the positive real line. And it is defined to be the point in time that the point is disconnected from infinity by the curve. So this is illustrated into, so in the figure it is showing eta stopped at tau sub x in two different examples. And in the right of these examples, we consider a space filling curve, and I have assumed that this space filling curve is hitting the points on the real line in increasing order. So we will start by looking at, we will start by proving this first lemma. So first we observe that without loss of generality, we can assume that x is equal to 1, because by scale invariance of SLE, we know that the lemma holds for x equal to 1, if and only if it holds for general values of x. And then we write down the Loewner differential equation for the point x equal to 1. Then we define y of t to be the denominator on the right side of the Loewner equation, modulo multiplication by root, modulo division by root kappa. So in the figure, you can see that we have mapped out the SLE curve at some time t. And you can see that on the right figure, there's a red point and a black point, which are the images of the corresponding dots on the left figure. And you can see that y of t, modulo multiplication by root kappa, then y of t is describing the distance between these two dots. So then next I'm claiming that tau sub 1 can be equivalently defined to be the time that y is first hitting 0. So y hitting 0 is equivalent to the denominator on the right side of the Loewner equation hitting 0, which is equivalent to the Loewner equation no longer being well defined. And we know that k sub t is the set of points for which the Loewner equation is no longer well defined. So this observation is justifying this alternative definition of tau sub 1. So then by using the Loewner equation and the definition of y, then it's possible to argue that y is satisfying the shown stochastic differential equation. And for some of you, this stochastic differential equation may look familiar because it is exactly the differential equation of a Bessel process. And it is a Bessel process which has dimension 4 divided by kappa plus 1. So it is a well-known result that the Bessel processes have a phase transition when the dimension is equal to 2. When the dimension is smaller than 2, then the Bessel process is hitting 0 infinitely often, while when the dimension is greater than or equal to 2, then the SLE, then the Bessel process does not hit 0. And when the dimension is strictly bigger than 2, the Bessel process is even transient. So this phase transition at dimension equals 2 for the Bessel process, that translates to a phase transition at kappa equals 4 for the SLE. Okay, so this was the first lemma. So then we have proved the second lemma on this slide, and we will use that to deduce the first lemma. And we first look at the case when kappa is between 0 and 4, which is illustrated in the top figure. So to prove this lemma, we first look at the case when kappa is between 0 and 4, and then we choose some time t. We run the curve until time t, and we map out at time t. So then by the domain Markov property, we know that the red dashed curve in the right part of the figure will have the law of an SLE in the upper half plane. And we know by the second lemma that this SLE will almost surely not hit the real line. So in particular, this SLE will almost surely not hit the blue part of the real line. So if we translate what this means in the setting of the left figure, we see that it means that the red dashed part of the curve will not hit the initial blue segment of the curve. And then we can repeat this argument for all rational times t, and we can conclude from this that the SLE curve has to be simple. So the case when kappa is bigger than 4. So I will not give you all details of that proof because it's very similar to the first part. So again, the idea is just to run the curve up until some rational time t, then map out, and then see what the second lemma is telling us about the SLE in SLE, which has been mapped out. Okay. Yeah, so that's what I want to say about the phases of SLE. So I think we can take a little break of a few minutes now in case there are any questions.
There are some questions in the chat, but I guess they're all kind of answered. But
okay, yeah, that's good.
So.
Yeah.
Okay, so we can take a couple of minutes break. Yeah.
Yeah.
So there is a question last question in the chat which is not yet answered. Is there an intuitive way of seeing why the SLA behavior should have a phase transition for some kappa?
I'm not sure. It's so I guess what the question is whether one can see just from the definition via Loewner chains whether there should be a phase transition for some kappa. So I think at least I don't know any very intuitive way to see directly just by looking at the Loewner equation and without doing any sort of computations. Or I don't see exactly. I don't see any way to see it directly. Maybe some other people who are listening have some thoughts of this, but yeah, I don't know it myself.
Okay. Yeah, but I don't know if I have the power to do that.
So,
Thomas maybe could do that. Of unmuting all the participants. I'm not sure. I'll try.
yes, I guess Matte's point is that if you if you somehow define SLE to be the scaling limit of discrete models, then one can see from in that sense that there should be scaling limits because one can deduce by properties of the discrete models that their limiting curves should satisfy some qualitatively different properties. Yeah. So I guess I guess it depends on what definition we take of.
Yeah, but it's not clear why there should be like monotonicity in K in kappa, right? Because this somehow like Matte's argument somehow suggests that there's some self-touchiness should increase in kappa.
Yes, of course, from discrete models, that's not clear at all because yeah, for the discrete models, it's somehow yeah, because of course the discrete models converging to SLE. I mean, typically, it's completely different models for different kappa, so the monotonicity is not so it's not really clear from that point of view.
Is there any kind of connection between the like physical characterization of critical behavior via conformal field theories to this kappa, like saying like kappa is the central charge of the
yeah, so that's possible to do. So there is a relationship between kappa and the central charge. So I think kappa equal to 4, corresponding to central charge equal to 1. And then for the other SLEs, then they correspond to central charge smaller than 1. And there is a duality relationship. So both SLE kappa and SLE 16 over kappa, they correspond to the same central charge.
Okay.
Yeah.
Cool. Yeah.
Okay, so maybe one last question in the chat. It says that is there a driving function? Is there a condition on the driving function which ensures that the corresponding SLE is a simple curve, SLE or whatever you want to call that?
Well, so I guess of course the proof that we looked at now is showing that that depending on the value of kappa in the driving function, then so it shows that there is a direct relationship saying that if kappa is smaller than or equal to 4, then it's simple, and otherwise not.
Yeah.
Yeah.
Okay, so maybe we should. Okay, so Omar has an answer.
Okay.
So the process is Holder alpha with alpha bigger than half, then the curve is simple.
Yes, okay. but Brownian motion is exactly
critical,
exactly
not.
So
it's
so
not
then
clear.
It depends on kappa.
Yeah, exactly.
Okay, yeah. I think we should resume and postpone all the other questions till the end of the lecture. Okay, so.
Okay.
Yeah.
Yeah. So then I will continue. So the next property of SLE that we will be looking at is locality of SLE6. So it turns out that certain particular values of kappa have very particular special properties, and one example of this is locality of SLE6. So we let eta be an SLE6 in the domain D from x to y. Then we assume that y tilde is some other boundary point, and then we let tau be the time that eta of t is hitting the arc between y tilde and y. So that we choose the arc not containing x. And then we define eta tilde and tau tilde in the same way, except that now we let eta tilde be an SLE towards y tilde instead of y. And then locality, it means that eta until time tau is equal in law to eta tilde until time tau tilde. So here we view the curves modulo a reparameterization of time. So as you may recall from earlier, the percolation interface on the triangular lattice is converging to SLE6. And we can see that the percolation model is satisfying a variant of locality in the discrete. So here we are considering a percolation interface, but I haven't specified whether the percolation interface is towards y or y tilde. So therefore, you can see that the vertices between these 2 points are colored in gray. The color is not known, but otherwise, the color of all the other vertices are equal in law, independently of whether the percolation interface is towards y or y tilde. So therefore, we see that percolation interfaces between y and y tilde, they can be coupled together. So they are identical until they hit one of these, or until they encounter one of these gray points. So this is the exact discrete analog of locality. So to prove locality, one way to do it is to consider an SLE6 in the upper half plane towards infinity. Then choose some point y on the negative real line, and then prove that this SLE6 it has the law of an SLE which is towards y instead of infinity, until eta is hitting this half line L, which is between y and infinity. So I will show you a quick sketch of how one can prove this. So the figure is illustrating the setup of the proof. So we let eta be this SLE in the upper half plane towards infinity. We let g sub t be the mapping out functions, and we let w be the driving function. Then we let phi be some conformal map from the upper half plane to the upper half plane, sending the origin to the origin and y to infinity. Then we let eta star be the image of eta under the map phi. So then we let g star sub t be the mapping out function of the curve eta star until time t. And then I claim that these functions, g star sub t, that they satisfy some variant of the Loewner equation. So I claim that they satisfy the variant of the Loewner equation shown in the indented equation. So this is exactly the standard Loewner equation, except that on the right side, you can see that instead of being just a constant 2, there is the derivative of some function b. So the reason we need to modify the Loewner equation in this way is because when we've considered curves before, then these curves have been parameterized by half-plane capacity. But now we see that this curve eta star will typically not be parameterized by half-plane capacity because it inherits the parameterization from eta. So therefore, we see that we need to modify the speed of this Loewner flow to take into account that the half-plane capacity that eta star is not parameterized by half-plane capacity. Then we let w star denote the driving function of eta star. And then we see that w star is equal to phi sub t composed with w. And this follows simply from, this is simply because the figure, the various conformal maps on the figure commute. So now what we want to show is that the curve eta star has the law of an SLE6 towards infinity in the upper half plane until it hits L star, which is the image of L under phi. So why is this what we want to prove? So you may remember from the previous slide that what we want to show is that eta has the law of an SLE6 towards y until it hits L. So by using the definition of eta star, this is equivalent to showing that eta star has the law of an SLE towards infinity until hitting L. So this again is equivalent to showing that W star is this particular time change of a Brownian motion. So why is this sufficient? So we know that eta star is an SLE if and only if it satisfies the Loewner equation, where the driving function is the constant multiple of a Brownian motion. So in our particular setting, we see that eta star, since it's not parameterized by half-plane capacity, then what we want to show is that that its driving function is this particular time change of a Brownian motion instead of being an exact Brownian motion. Okay, so I will not show you exactly how you prove that W star is this particular time change Brownian motion. But the idea of the proof is to use Ito's formula and to use that W star is the composition of phi sub t and W. So when you use Ito's formula, then the drift term of W star will contain both time derivatives and space derivatives of phi sub t. And in order to show that the drift term disappears, you have to prove and use that the time derivative and the space derivative are shown by the related equation. Yeah, but I will skip the details of this, and I just refer to the references that I gave. Okay, so now we have seen that SLE6 is the unique SLE which satisfies the locality property. Another important property which is satisfied for one particular value of kappa is the restriction property. So I first define what the restriction property is. So we let D be some simply connected domain and X and Y be boundary points. And then we assume that mu sub D comma X comma Y is a family of probability measures on a curve in D, and curves in D connecting X and Y. Then we assume that eta is sampled from one of these measures, and we'll let U be some simply connected domain contained in D, such that X and Y are boundary points of U. Then we say that our probability measures satisfy the restriction property if the curve eta, conditioned to stay in U, has the law of the curve, which has been sampled from the measure in U. So then I asked below the definition for which kappa does SLE kappa satisfy the restriction property. So I will come back to this question a little bit later, but I want you to keep it in mind for now. Yeah, and you can think about it while I go through the next slide. If you have some guess for which kappa value it is, and you see why, then you can write it in the chat. At least if you haven't seen it before. Okay, so on this next slide, we will be looking at the restriction property in the setting of some discrete models. So the first question I ask is whether this loop-erased random walk is satisfying the restriction property. Okay, so we consider some simply connected domain D with marked points A and B and some discrete approximation. And then we'll let W hat be a simple random walk, which has been started from the point A sub M, and which such that we condition the random walk to first to leave the domain D or to leave D sub M at B sub M. And then we let W be the loop erasure of W hat. So we simply erase all the loops that W hat has created, such as we saw in yesterday's lecture. And then we let U sub M be some connected subset of D sub M, with such that A sub M and B sub M are contained in U sub M. And now we see that the loop-erased random walk is not satisfying this restriction property, because the loop-erased random walk in D sub M, conditioned to stay in U sub M, is not the same as the loop-erased random walk in U sub M. And the reason is that for the latter walk, we require that this simple random walk W hat is staying in U sub M, while for the former walk, we are only requiring that W is staying in U sub M. So since these requirements are different, then the loop-erased random walk does not satisfy the restriction property. Okay, so then we look at the self-avoiding walk. So we remember that the self-avoiding walk, it has been sampled such that the probability that the walk is equal to some fixed walk little w is proportional to mu to the power minus the length of w, where mu is the connective constant. And what we see is that this self-avoiding walk, it does satisfy the restriction property. And the reason is that the self-avoiding walk conditioned to stay in U sub M is equal to the self-avoiding walk in U sub M. So how can you see this? So when we condition the self-avoiding walk to stay in U sub M, it simply means that there are certain paths that we're not allowing. But if we look at the set of paths that are still allowed, then each of these paths will still have a weight mu to the power minus the length of the path. So we see from this that the restriction property is satisfied. Okay. Yeah. So yeah, I guess I can go back to the previous slide. Yeah. So I don't think there have been any comments in the chat. But you may remember from earlier that I said that the self-avoiding walk is believed to converge to SLE with parameter kappa equal to 8/3. So this may lead you to guess that it should be the SLE with kappa equal to 8/3 that satisfies the restriction property. And this turns out to be correct. And this is also the exact reason that the self-avoiding walk is believed to converge to this value of SLE with this value of kappa. So here I've stated the restriction property for SLE 8/3. So we consider an SLE in the upper half plane from 0 to infinity, we'll let K be some subset of H, such that H minus K is a simply connected domain, and such that K is bounded away from 0 and infinity. So then the SLE conditioned not to intersect K has the law of an SLE in the domain we get by removing the set K. Okay, so the proof of this property is done purely in the continuum. So the first thing one can observe when doing the proof is that the proposition is equivalent to proving the indented equation A. So this is saying that we assume that K prime is some set containing K, which is on the same form as K. And A is saying that the probability that eta avoids K prime, condition that it avoids K, is equal to the probability that eta avoids the image of K prime after mapping out K. So why is this equivalent to the proposition? So the probability on the left side, so we can use that probability to characterize the law of eta conditioned to avoid K. The reason is that we can characterize this law by varying the sets K prime. On the other hand, the probability on the right side, it's characterizing the law of an SLE in the domain obtained by removing the set K. Okay, so this so we have now argued that proving A is equivalent to proving the proposition. So then there is a key identity which will be used in the proof, which is saying that the probability that eta avoids K it's equal to the derivative of the mapping out function at 0 to the power 5/8. So here G tilde sub K is denoting the centered mapping out function of K. So I will not do the proof of this identity, but I can mention that just like the other proofs you have seen today, it's done by stochastic calculus, and it's done by defining a particular martingale, which is equal to the probability that eta avoids K given the SLE until some time t. Okay, so it turns out that this equation A is actually an almost immediate consequence of this key identity. So first we can use Bayes' rule to see that the left side of A can be written as the ratio of two probabilities. Then we see that A, after we have done this transformation, then A describes the relationship between three different probabilities, where all these probabilities are on the form of the probability in the key identity. So then we can also use that the mapping out function of K prime is the composition of the two other mapping out functions that we're interested in. And then we can use this together with a train rule and the key identity to get the indented equation A. So one small remark is that in this proof, this exponent 5/8 in the key identity is not really important. So the proof would have carried through in the exact same way if this exponent 5/8 had been replaced by some other exponent alpha. And it turns out that the key identity with some other exponents, this corresponds to other sets that also satisfy conformal restriction. If alpha is this exponent alpha is strictly bigger than 5/8, then these sets will no longer be simple curves. They will be some other simply connected sets that connect 0 and infinity in the upper half plane. Okay, so I will also just give a short remark, which is that so far in the talk we have been studying chordal SLE, but there are which connects to boundary points of a domain. But there are also other variants of SLE known as radial and whole plane SLE. Which are SLEs where one of the two endpoints are interior. One or both of the two endpoints are interior. So I'm mentioning these curves briefly because the whole plane SLE will be mentioned in tomorrow's lecture. I will not be saying much about these curves, but I can say that they're also generated by some variant of the Loewner equation. They're also associated with a parameter kappa, and for each fixed value of kappa, then there are closer relationships between a chordal SLE kappa, radial SLE kappa, and the whole plane SLE kappa. Finally, I want to mention a few open problems. As before I start to present these, I want to mention that the selection of open problems is somewhat arbitrary, and it's not necessarily the most important open problems about SLE. But the first class of open problems I state is convergence of discrete models. There are convergence to SLE has been proved for some discrete models. But there are still many models for which convergence to SLE is conjectured but not proved. We have already looked at the self-avoiding work. Another open problem is universality for percolation, which means to get some variant of Smirnov's result for percolation on the triangular lattice to percolation on other lattices. For example, one can consider bond percolation on Z2. So this is illustrated in the figure. So we have a domain with two marked points, A and B. On one boundary arc between A and B, the edges are blue and open, and on the other boundary arc, the edges are closed and gray. And otherwise, all the edges are open and closed with equal probability, and independently with equal probability. In this figure, I have looked at all the edges which were closed, and I have drawn a perpendicular orange line segment on these edges, and then we get this picture. And then in this picture, it's possible to draw the interface between blue and yellow, which is a curve connecting A and B. And it's believed that this curve is converging to SLE6 in the scaling limit. So this is just one of the many other percolation models which are also believed to converge to SLE6. Another model is the FK percolation model. So these first three examples on the slide, so they are some of the big open problems in SLE. And one of the well-known big open problems in SLE regarding convergence to SLE. So this fourth model I've stated here is not as well-known. It's not as well-known that it's related to SLE. But there are still convincing simulations. So what is so in the left part of the figure, we consider the 6-vertex model. So we consider Z2, and each edge is directed such that at each vertex, 2 edges are incoming and 2 edges are outgoing. So you can see that at each fixed vertex, there are 6 possible configurations. So it turns out that if we're given such a configuration of the 6-vertex model, then that can be associated with a certain space-filling path. So that's obtained by looking at the outgoing arrows and then bending the tip of the outgoing arrows. Then we get this space-filling path. And this is conjectured to converge to SLE. So if the 6-vertex configuration is uniformly at random, then one should get SLE 12. But by varying the parameters of the 6-vertex model, one should get a range of kappa values. So then there is so all these 4 models stated here. So proving convergence on regular lattices is open, except for the case of side percolation on the triangular lattice. But for all these 4 models, convergence result has been proven on certain random lattices known as random planar maps. So I will not go into details about how the random planar maps have been sampled or drawn. So for now, just treat the random planar map as some random lattice. So for all these 4 models, convergence result has been proven on such lattices. And I can mention that one reason that the models are sometimes easier to analyze on random lattices than on deterministic lattices. It's because these random lattices, they satisfy some, they often satisfy some useful Markov properties. So that's one class of open problems. Another class of open problems is about statistical physics models in higher dimensions. So many of the models converging to SLE also make sense in higher dimensions. So in very high dimensions, they can often be understood via lace expansion, but in small dimensions, bigger than 2, then these models are often very hard to analyze. The loop-raised random walk and the uniform spanning tree, they have been proven to have scaling limits in 3D, but it's still an interesting open problem to give, but these results, they only give the existence of the scaling limit, but they don't give an exact, they don't give an explicit description of the limiting objects. So this is still an interesting open problem. Percolation can also be defined in 3D. So here you can see in the figure an example, a model known as tricolor percolation. This has been studied in physics, and the simulations show that it has some interesting behavior, including phase transitions, but there are very few results which have been proved rigorously about this model. Then third type of open problems is to prove properties of the SLE curves. So here I could have mentioned a lot of different problems. You can just use your imagination to find interesting problems. But I mentioned one example, which is to understand the to prove existence of the Hausdorff measure of SLE. So it has been proved that the SLE has a well-defined and non-trivial Minkowski content of dimension 1 plus kappa over 8. This was proved by Lawler and Reza. But it has not been proved that it has a Hausdorff measure. So the Hausdorff measure is defined in terms of covers of the curves by balls of varying size, and it's difficult to understand this because it involves this optimization problem over these balls. Okay, so I think yeah, that's all I wanted to say today. So yeah, if people have any questions, then
so,
and I ask them.
So I'll unmute the audience to. So we should thank Nina for the lecture.